Okay, so this section is data sets. This section also is going to take us a little bit of time. It's a longer section, and you'll understand why by the time we're done. So by the time we're done, I want you to be able to describe the data set naming rules. I want you to be able to describe what a partitioned data set is. Describe a sequential data set. How's that different than partition? Describe a VSAM data set. How is that different from the sequential and partition? I want you to be able to describe what I mean by a data set extent. I want you to be able to describe the role of something known as a system catalog in the user catalogs. I want you to be able to describe the role of something called a VTOC. And then describe the ZOS-based Unix file systems. How do we do it? By the time we're done with this, you'll have more in-depth knowledge about all of these things. Let me go ahead and get started. So what is a data set? Well, in the Unix and Linux world, it's commonly called a file. But the word data set actually existed 50 years ago before Unix and Linux. We called it a data set, a set of data. So this is a data set is a collection of logically related data records. Now, I actually emphasize that word data records for a reason, and I'm going to be describing that more later about records. So these data records are stored on disk or on tape, and it can be spanned across disk or tape. Known in tape volumes and disk volumes are commonly called volumes. So when you use the word volume, it could be a tape volume or a disk volume. So a data set, of course, a data set can store a source program, just regular data records. And as you've seen, you can print data sets or you can display data on your terminal. Now, there is a statement down here that's very important. A logical record is the basic unit of information used by a program running in ZOS. Let me break that down for you. What a logical record is. The logical record has a size to it. And that size is called the logical record length. The best way for me to begin to go further with this is in the Unix, Linux, and other environments, everything is a stream of bytes. Even memory is a stream of bytes. Devices are a stream of bytes. Data that's stored on disk is a stream of bytes. That's why you'll see the carriage return new line ASCII characters at the end of something so that it can go to the next line, because everything's a stream of bytes. In ZOS, we do not have carriage return new line because everything is record oriented and it has a length. So a logical record has a length and the program can read it. And it knows where the end is because the system has an attribute of that data set and says the record length is this. So when the program reads it, it knows where the end of the record is. So a logical record is the basic unit of information used by a program running in the ZOS environment. So how data is stored? Well, obviously you can store data on disk or tape or even optical. The programs and the system utilities can store and retrieve records either directly or sequentially. And I'll be talking about what that means later, the difference between directly or sequentially. So programs and system utilities use disk volumes for storing data and executable programs. The operating system itself is stored on disk because the mainframe, there's no disk inside the frame. All the disk is connected by fiber optic that I actually pointed out earlier in our first session when I talked about overview of the System Z environment. So your operating system's on disk. It's paramount to taking your PC and removing the hard drive. The hard drive's got your operating system. Well, the hard drive of the operating system of the mainframe sitting on disk that's fiber channel connected. Data management. So I'm not going to read verbatim here what data management's all about. However, I will let you know when a lot of people went to the distributed world and PCs were fairly new, everybody thought they were cheap nips and thought, well, let's get off that expensive mainframe and go to this distributed environment. Well, the first mistake that many of them made is they didn't understand all these disk management disciplines. They didn't understand backup, migration, placement. Also, they didn't understand security. A lot of people made a lot of mistakes going to distributed environments from the mainframe. They also discovered it wasn't so cheap. They discovered that actually it was more expensive. And today, it definitely is more expensive because of many different reasons, such as power. A lot of people are now consolidating back to the mainframe rapidly. Right here where my cursor is, in ZLS, one of the base elements, or base component, and I actually shouldn't call it a component because it turns out that DFSMS has multiple components. And so the base includes DFSMS. And DFSMS stands for Data Facility Storage Management Subsystem. However, DFSMS is an umbrella of components. And we'll talk about that more later. But whenever you think about dealing with disk volumes, dealing with tape, dealing with the data access methods, dealing with utilities, many of the utilities, they're in the DFSMS bookshelf. So think DFSMS when you're thinking data. But it's part of the base of the ZOS operating system. There is a term called DASD. It's a throwback term. When the physical device was different, but you'll hear that term, DASD, and they still use it, and it stands for Direct Access Storage Device, and you'll still hear that term used, but it just means disk volume. Now, it turns out, like any other operating system, the disk volumes have a geometry. The disk geometry has cylinders, and then the cylinder has a size, and then there's tracks inside the cylinder. The track has a size, and the tracks are what contain the records. Now, one thing that's different about ZOS that kind of is a new paradigm for many people that are only used to Linux, Unix, or Windows, the way all data is presented all looks the same. In Unix and Linux, there's a thing called PFS, Physical File System. It's the data access method. And inside of there, if you break it down, for those of you that know Unix and Linux well, there's these things called inodes and super blocks and other things that kind of make up the characteristics of the data access method. Well, in ZOS, we have multiple data access methods. And so the characteristics of storing the data are different depending upon the data access method being used. Well, why is this? There are several different reasons. One of which, and I mentioned this early on Monday, when mainframes were first built 50 years ago, they were an expensive proposition for businesses, but businesses had to get them to be competitive. Well, what we promised business at the time is we said, we'll protect your investment in the mainframe. Anything that works now will work in the future. The different data access methods that we had were considered non-VSAM. The types of non-VSAM data sets are sequential. What sequential means, it's really truly like a file. You have a name, and if you view that name or edit that name, you have the data. So a sequential has a single data set name, and if you look at that data set name, you find a collection of records, whether it be a program, whether it be an executable, whether it be just data. Then we came up with something called a PDS, a partition data set. And it has something we refer to as a partitioned organization. It consists of a directory, and so the data set name, if you go to look at it, it has members inside of it. You look at the member, and the member has the records. We also then came up with something called a PDSE, Partition Data Set Extended. It has faster directory searches, and it has reduced maintenance. What do I mean by reduced maintenance? Well, it turns out that partition data set, the PDS, as you updated it or changed things, you would waste space inside of there. And so they had to do what was called a compress to regain the wasted space with as you updated members. A PDSE automatically regains that space. So these are three examples of non-VSAM data sets: sequential, partitioned, and partitioned extended. But then we created something called VSAM. Why did we create VSAM? It's a superior data management mechanism. And when we created VSAM, it's very fast, and we have different types of VSAM. We've got something called a keyed sequential data set, an entry sequential data set, a relative record data set, and a linear data set. I'll mention this now. It turns out that the linear data set is how we actually create Unix file systems. Also, you're going to see in DB2, when we create DB2 table spaces that stores tables, they're actually really VSAM linear data sets. The difference between a linear data set and the KSDS, the ESDS, and the RRDS is that in those first three, there's metadata inside the VSAM data set that talk about the attributes of the records inside of there. A linear data set has no metadata inside the VSAM. It says whoever's going to put things here, they're managing it, like DB2 or Unix. How do you allocate space? Well, when you allocate space, and what I mean by allocation here, I'm thinking of a new creation. You need space. So you can do it explicitly or implicitly, and here's what I mean by explicitly. In JCL, you can actually say in the DD statement, I want space, and you can tell it how much space you want on disk. But when you give it space, you also give it, where do I want to store it? On some tape, on some disk. But there's a TSO allocate command, which is one of those command line interfaces. You can actually say allocate, and there's allocate operands to create space on disk. Also, there actually is a supervisory routine. If you're writing an assembler, there's an SVC99 that within the program you can allocate a data set and give it space. There's another system utility called IDC AMS, IDCAMS. And oh, by the way, IDC, the first three characters is the component. IDC AMS, IDC Access Method Services, is how you define VSAM data sets. Now, this is a way to explicitly say, I want a data set on disk or tape. I'm going to tell you what I need and give you the attributes. Well, many, many years ago, it turned out that, and this is a true story, the developers used to complain sometimes when they couldn't deliver applications on time. They would actually say, well, we got to worry about all this stuff in JCL, like how much space to use and what disk to put it on. So IBM created something called DFSMS. And inside of DFSMS, there's this thing called the Automatic Class Selection ACS routine. So now the disk storage administrators could actually write rules, very easy to write, and say, okay, developers, you no longer have to worry about how much space you need, where we're going to place it. We're going to take that from you. All you got to do is follow some very specific rules, and we'll give you the rules, and you follow them. And that will take, the DASD management people will take care, or the disk management people will take care of all that for you. It was very interesting. I know I had to present that to the development people when I first implemented it, and their jaws dropped because they thought, oh my goodness, here's what happened. I not only took away one of their excuses, but they loved having the ability to determine the amount of space and where they were going to put things. They loved the flexibility once they understood it. And once it was taken away from it, once that was taken away, I took away their excuse and their authority to do things. So it was just kind of interesting. Now, non-VSAM data set characteristics. As I mentioned, the smallest amount of data to be processed is a logical record. However, records can be grouped into blocks. What do I mean by that? Well, a program goes and reads a record from disk. If we allocate the data set and we say we're going to allocate a block, what a block is a block has so many records in it. And you can determine what the block size is. So if the data set is blocked, you have multiple records in a block, when the program goes to read the first record, the entire block is read into memory, not just the record. Because it may assume you want the next record. If you do not block things, it reads off of disk a record at a time into memory. If you block things, it reads the entire number of records in that block. That's for non-VSAM. VSAM is different. Records are stored in something called a control interval inside the VSAM. But the control interval can be so large that it could contain multiple records. It could contain one record. It could contain many records. And in some cases, you could have a record that's so big, it actually spans multiple control intervals. And there's actually a book that actually shows a picture of all this that I'll be bringing up a little bit later. So how data sets are created on disk? Well, data sets are assigned disk space in chunks called extents. Every data set has a primary extent. Once that primary extent is full, then you can get a secondary extent. So when you allocate space, you can say my primary extent is so big, and my secondary extent has a size. When the primary extent is full and you get a secondary, you get a secondary. If that secondary fills up, you get another secondary. The number of secondaries you can get depends upon the data set access method being used. I think these days you can get up to 256 extents. Am I right about that, Larry? Is it 256 or even more now? Yeah. 255 extents. but the number of extents depends upon the data set access method being used. Now, here's an example of non-VSAM, data sets non-VSAM, and if I give it a record format attribute of fixed, every record has equal size, fixed length. Every record has a fixed length. Now, if I do fixed block, that's a record format of fixed block, there's a block size. And the block size is typically a multiple of number of records. So you might put 3 records in a block. Typically, it's a lot more than that. If you do fixed block, if a program reads the first record, the entire block is brought into memory. Do records always have to be equal length? No. You can have a record format of variable. That means the data set can have different length records in it, but each record, when you say record format of variable, the very first byte of the record is the length of the record. You can even have variable blocked. And then the very first part of the block will have the block size, and each record has the record length as part of metadata inside of the data set. There's another special type of record format called undefined, U. The undefined is almost exclusively for executable modules. The operating system knows how it's laid out because we go through a process called a link edit or binder to create the executable module, and we put it in an undefined record data set because there's metadata inside of there for the operating system to know how to deal with that executable module. So I already talked about partition data sets and partition data sets extended. PDS, a simple and efficient way to organize related groups of sequential files. Think of a sequential file as a member. But a PDSE, it looks and feels just like a PDS, but the space is reclaimed automatically when a member is deleted, and it has faster directory searches. VSAM. Now, one thing about a VSAM data set name is accessed by the access method, and the way the system accesses VSAM is through something called a cluster name. Why cluster name? Because a VSAM cluster name can be associated with one or more physical data set names. An example, well, one very simple VSAM is called an entry sequential data set. So there's a VSAM cluster name, but it turns out that an ESDS has a physical data component, and the data component's a data set name sitting on disk, but it's referenced by a cluster name. Just remember that because I'm going to be talking about catalogs later, how data sets are located, and this cluster name plays an important part. Now, a VSAM KSDS, it has a cluster name, but when you reference that cluster name, there's a physical data component and there's a physical index data component. There are 2 separate physical data sets on disk. Each one has a primary extent and potentially multiple secondary extents. So a KSDS has a data component and at least one index component. It optionally can have other alternate index components, which is a separate physical data set, all referenced by a cluster. So VSAM, as I mentioned earlier, VSAM data sets are a collection of records grouped into control intervals, known as a CI. with the exception of a linear data set. Linear data sets are different. They don't have any metadata in them. A control interval, CI, is a fixed area of storage space in which VSAM stores the records. It turns out if a control intervals are grouped in contiguous areas of storage called a control area. Now, you can get additional control areas. And I'll be talking, actually there's a book that describes it that I'm going to point out to you in a minute. So some of this is a repeat. The following are different types of VSAM datasets: KSDS, ESDS, RRDS, and LDS. And as I mentioned earlier, a special system utility, IDCAMS, IDC AMS, Access Method Services, is used to define, delete, rename, and copy VSAM datasets. And of course, programs can read them or write to them. There's an excellent red book called VSAM Demystified. If you want to know about that metadata inside of there in a control interval and control area, this has diagrams inside of it. There's also, in the DFSMS bookshelf, there's a couple manuals in there that go into great detail also about how VSAM really works. But I would recommend for new people to look at the red book and look at this red book, VSAM Demystified, to look at the details of how VSAM works. It has diagrams in it. Okay, I'm going to switch gears on you. Let's talk about a data set name. So a data set name, we're not talking about the data now, just the data set name. And I say each catalog data set name, and I'll explain catalog coming up, but each data set must have a unique name, a maximum of 44 characters. So a data set name has a maximum of 44 characters. However, you can't just say A through Z, and it turns out that a data set has a maximum of what's called 22 name segments. The segment, sometimes called qualifiers, are separated by a dot. So you've got a name, dot, name, dot, name, all the way up to 44 characters. Here's an example of a data set name, zIBM 000.jcl. Notice the dot. There's two qualifiers. The high-level qualifier, HLQ, is zIBM 000. So that is a segment. So the first name in the left is considered the high-level qualifier. Then the dot will separate the high-level qualifier from other qualifiers. The very last qualifier is considered the low-level qualifier. Everything in between is considered a middle-level qualifier. So these qualifiers can be from 1 to 8 characters. The first character must be alphabetic or one of these special characters. The remaining 7 characters of the qualifier can include numeric or a hyphen. Data sets are uppercase only. The dot is part of the maximum length. That's why we say that you can only have 22 name segments. The dot is part of the length, maximum length of 44. So those are the rules for data set names. Okay, a partition data set. Partition data set member names. A member within the partition data set, the members follow the rules of a qualifier. A member is a maximum of 8 characters in length. but it can be a single character. And so just the member names themselves follow the same rules as a data set qualifier or segment. Now, you're observing at our ISPF primary option menu. Now you know the 3.4 panel is one of the very commonly used panels to get a data set list. This is a pattern matching. If I say I want all data set names that begin with this, then what it does is it actually comes back with a list of data sets that match that pattern. However, I want you to observe over on the right this volume column. Well, these volumes, these are labeled by a system programmer. System programmer decides what the label of the disk is. But you'll observe one of these says asterisk alias. That's not really a volume. These are physical volumes. This is where the data is physically stored. I'm going to be explaining some of this to you. I'm setting you up to explain some things to you. So these data sets are sitting on a volume. That volume could be disk, that volume could be tape. If I do F11, remember I mentioned that in ISPF, many times you're looking at a piece of the window, and you can sometimes go up, down, right, and left to look at more information. Well, when you're on that 3.4 panel, if you do an F11, it will shift you to the right, and you will see more information. For example, the record format, fixed blocked, and things like the record length. In this case, it has a record length of 170. And this record length of 170, it's fixed. Therefore, the block size is equal to the record length because it's fixed. The data set organization, this PS stands for physical sequential. What is sequential data, and we're going to be using this data set, it's sequential. So if I view it or browse it, there's just data records inside of it. Here's an example of a record format fixed blocked. The record length is 80, and it has a block size. This POE is partitioned organization extended versus a PO, which is partitioned organization. Now, I'll mention this now, and I'm going to mention it again. Both PDS and PDSE are loosely called libraries. Why library? It's a collection of members, a library of members. With that being said, that PDSE and PDS are called libraries, there actually is a JCL reserved word called library. You can say DSN type equal library. When you say DSN type equal library, it automatically creates a PDSE. However, both are loosely called libraries. I just want you to know that there is a JCL reserved word called library that specifically will allocate a PDSE. Now, if I am on the 3.4 panel, and in the command column, I put an I for information to the left of a data set, it's going to display information about that data set. In this case, here's the data set name. It says it's on this volume. The device type is a 3390. All of our disk device types are now 3390. Partition sequential, or excuse me, physical sequential. Record format fixed, record length 170, block size 170. And notice here, first extent, cylinders 2. That's the primary extent. What if I need a secondary extent? Just give me 1 cylinder. And then it talks about how much I've got allocated. Also, there's metadata here. There's a creation date. There's a reference date. Where does that information come from? Is that metadata inside the data set? No, it's not. But I'm going to be able to, I'm going to explain where this metadata about the data set is stored. Now, another thing that I'm doing here, I'm putting an E, edit, to the left of this data set. We did this yesterday, and if I do edit, I'm in edit mode on this data set, and it's obviously a partition data set because it's got members. I can select one of the members. This is what we did yesterday, where we created edit test with the ISPF editor and put data inside of it. If I edit that, I'm in edit mode on the data set, open parentheses, that's the member name. Inside of there is the data records. Here's the data records. Okay, now I'm setting you up for more metadata. In this data set list utility panel, we've always been using this DS name level field. Well, let's say, for instance, I keep that blank, and I put a volume in there, something that we've labeled. I happen to know that there's a volume, and I'm not sure if this is on our lab system or not, but this volume label, it's something, it's a disk volume, and if I do this, then it comes back with a list of data sets on that physical volume. So it went to the volume and said, tell me all the data set names on that volume, is what it did. Another thing that I can do in the 3.4 panel, as I mentioned, it's pattern matching. I want all data sets to begin with MVS. It gives us a list of data sets that begin with MVS. But one thing that I want to point out here, there's a special data set, mvs.global.csi, and notice there's an mvs.global.csi.data and an mvs.global.csi.index. Well, if you look at the volume column, see this asterisk, VSAM asterisk? That's not physically on the volume where the data is. The asterisk VSAM asterisk is a cluster name. The real data that's on the volume is right here. So on this volume, VD MVSG is the data component and the index component that if you ask for mvs.global.csi, what you're presented is a KSDS with data and index for speed. Another thing that you can do with the 3.4 panel, you can actually enter commands to the left of the data set name. Remember yesterday, we got on TSO, and we did a LISTC command. The LISTC stands for list catalog. And if I overtype, I just say LISTC, ENT is abbreviation for entry, open parentheses slash, close parentheses, space all, and I just overtype it. The slash says, I want information about the data set on this line. That's what the slash is. So it's a real fast way. So list catalog, and give me the entry, this particular data set entry. And it came back and said, it's a cluster. And it's in catalog, catalog.os390. I'm going to be explaining what that means a little bit later. But it's the LISTC command again, list catalog. It also includes more information. It says associations of the cluster. Here's the data component. It's called mvs.global.csi.data, and here's the index component. Then it gives information about the data component, And it gives information about the index component, such as records deleted, records inserted. This is the KSDS, the key length. More information, that's got the index. So I'm going to move on. Now, it turns out on that 3.4 panel, you can actually wildcard in there. If you do F1 for help when you're on that DS name level field in 3.4, there's all kinds of wildcarding you can do for pattern matching. And I won't get into all the things you can do. One thing I want to point out, every disk has a VTOC. Every volume, disk volume, has a VTOC. A VTOC stands for Volume Table of Content. So what happens is, if you go to that disk label, the disk label goes to the VTOC. And the VTOC, kind of like the Windows NTFS or FAT table, it says, I physically know where that data set begins and where it ends. So the VTOC knows the physical placement, is taking care of the physical placement of the data on disk. There's another thing called a catalog. The catalog contains a data set name and it contains the volume that it's on. So if you create a new data set name and it places it on a disk volume or a tape volume, the catalog knows the volume name. From that point forward, when you ask for that data set name, you do not have to give it the volume name because there's thousands and thousands of volumes, both tape and disk. You give it the data set name, it goes to the catalog says, oh, that's on this volume label. It goes to that volume label, and let's say it's a disk. Then it goes to the VTOC on the disk, and the VTOC says, I know the placement of that data set on this disk. The VTOC not only keeps track of the data sets, obviously it keeps track of the free space, so that allocating new data sets on that disk. Now, this one here is an important diagram, because what it's doing, that each disk has a label, then the label points to the VTOC, but the important thing about this, I want to explain extents. So a data set, let's take my.data. My.data will have an extent, a primary extent. An extent itself, is a contiguous area on disk. It has a beginning and an end, and everything from the beginning to the end belongs to that extent. So it has a beginning physical part and an end. So let's say my.data, this is the primary extent. We give it a space, it's contiguous, but if the primary extent runs out of room, it's given a secondary extent. The secondary extent is a different physical location on disk, but the extent itself is contiguous. So in this case, your .data only has a primary extent. So on disk are extents. Each extent is contiguous, and it's owned by a data set name, and you'll have at least one primary extent, and you could potentially have one or more, in some cases up to 255, secondary extents. So a primary extent has an absolute size that's contiguous. A secondary extent has an absolute size that's contiguous. Each secondary will be the same size. But a primary can have a different size than the secondary. In many cases, what people do, they'll allocate a large primary, but smaller secondary sizes. The reason for that is it ensures you can find the area on disk, because if you've got a smaller size, it can find a place for it, because remember, it's got to be contiguous. If you ask for a giant secondary extent, it's got to find contiguous space on disk for it. So if you have a highly defragmented disk, it could be tough. But the DASD management people defrag the disk, just like we do in Windows. So what is a catalog? As I mentioned, a catalog really is another data set, but it's a VSAM data set, and it's considered to be metadata. There are catalog records that associate a data set name with a disk or tape volume. So locating a data set requires the data set name, the volume name, and the unit type. Why unit type? Because a volume could be disk or tape. And it'll say unit, and it's got a number there. I'll show you the device type in a minute. But there's a bit breakdown that says, oh, that's on tape or that's on disk. A zOS system includes a master catalog. You must have a master catalog. However, all data set names are not stored in the master catalog. The master catalog can be related to numerous user catalogs. And I'm going to explain the relationship. So in the master catalog, you can actually define an alias entry. What an alias entry typically is the prefix or high-level qualifier of a data set name. Then the alias is associated or related to a user catalog. So if I want to find zIBM000.jcl, it may go to the master catalog, and the master catalog says, well, I know about zIBM000, but I don't have all the information. I need you to go to this user catalog that the alias entry is associated with in the master. It says, go to that user catalog. That user catalog that I have you go to will have the entire data set name and the volume that it's on. That way you can have many, many user catalogs. And this is best to separate your user data from the system data sets. And you can have user catalogs by application, so it's a way to really organize things very nicely. And I can tell you, this ends up being important for migrating between releases. Because what you can do, you can actually connect a user catalog to a new master catalog, and there's all your data. The new master catalog is associated with a new zOS. What you can do, I'm in SDSF here, and from SDSF, I'm in the system log, and I issued a command, f-catalog, open. And it actually listed all the catalog names. So that's our metadata. And it told me the location of all those catalogs, and it gave me some other flags, and I'm not going to worry about that right now. But you can actually see which catalogs have been used. Now what I'm going to do, I'm at the ISPF primary option menu. I do a 6. 6 is equivalent to being in the TSO ready prompt. I'm just showing you another way to navigate. So it's a command. So remember, we did this under ready previously, but now I'm just doing the same thing using ISPF. So I type in profile. Notice my prefix is set to my ID. And remember, when you're in, if you see 3 asterisks, hit enter to continue. Now, I do a profile no prefix, no message ID, and this is a semicolon. I'm stacking a command. Then I type in profile again, stack a command, do a LISTC. So when I did that, it set the profile to no prefix. Then I did the LISTC, and this is that long list. So let me explain what we did yesterday and what we're looking at now. When I set the prefix to no prefix, it went to the master catalog. The first thing out of the master catalog is the master catalog name. Why does this cluster have all zeros? It's the master catalog. I'll just put it that way. These are the real data components for the master catalog. Then, in the master catalog, I'm doing a list catalog with nothing after it. It comes back and starts giving me entries in the master catalog, like an alias name. In this case, this is a non-VSAM full data set name that's in there. And this goes on and on and on, listing the master catalog, because my prefix is no prefix. There's also user catalog entries that are associated with alias entries. To break out of it, we had to find the PA1 to end that listing. Now what I'm doing, I'm setting my profile prefix to my ID, and I do a LISTC. What it did, it went to the master catalog and said, oh, zIBM 030 is in catalog, catalog.user.AA, and here's all the data set names in catalog.user.AA that begin with that high-level qualifier or prefix. In this case, it's also an alias in the master catalog. Now, what I'm doing here, I'm doing a profile no prefix, so I'm saying, hey, I want to talk to the master catalog. Profile no prefix, do a LISTC alias all. Give me all the alias names. And I put the word all in there also. Give me all information about the alias names in the master catalog. So the first alias, it came back and said it's accounts. In it, the associations are the user catalog is catalog.user.AA. And it does happen to know that catalog.user.AA, it knows what volume it's on. That doesn't show up here, but it knows the volume that it's on. So it lists all the aliases in the user catalog entry, and it knows the volume name that user catalog is on. Now, this is how simple it is. If I were to say, define this abbreviation, define user catalog, or UCAT, name it this, and notice I've got it in quotes. That's an absolute name. If I didn't put it in quotes, it will assume my set prefix. But the data set name in quotes is the absolute name. Define a user catalog, name it this, put it on this disk volume, and give it units of cylinders for space. That's the primary extent. And if you do need a secondary, give it an allocation of 1 extent of cylinder space on disk. Then if you do this, what it's doing, when I say define, it's actually behind the scenes executing a utility called IDC AMS, IDCAMS. Notice the message that comes back. IDC 0510I, catalog allocation status for that volume is 0. IDC, remember IDC, 3 characters? The module executed was IDC AMS. These are IDC messages. The name generated is catalog.zos.cat index. Now, I could turn around and define an alias, the high-level qualifier. I'm going to call it ZOS and relate it to that user catalog. Once again, if I do that, it's going to execute IDCAMS, and it's going to place that alias in the master catalog along with that name. So now, what you can do, there is a panel called a 3.2 panel that will actually issue a TSO allocate command to allocate a new data set. So if I go to the equal 3.2 panel, this is a data set utility panel, but here you can do an allocate a new data set, A for allocate. What do you want the data set name to be? Well, I want it to be absolute name zUS.test1, and I want you to place it on that disk volume. So if you do enter, it comes back and says, well, I need data set attributes. Here's the volume. What kind of units do you want for space? You want it in blocks, tracks, cylinders, kilobytes, megabytes, or records? Well, I just said cylinder. My primary quantity or primary extent is 1. My secondary extent or quantity is 1. I want it to be record format fixed blocked. I want the record length to be 80, but notice I did not give it a block size, because the best practice is if you fix block something, let the system compute the block size. Also notice I did not give it a data set name type. By default, it's sequential. So if I hit enter on this, it'll come back and say data set allocated. Now what I'm going to do is allocate another data set. I'm going to call it zUS.test2 on let me get the pointer here. I'm going to allocate zUS.test2 on a different volume label. Is a question? Yeah, I'm going to go to the chat. There's a question in there. How do I check which volume is usable? Great question. We're going to answer that, Robbie, we're going to answer that question a little bit later, because I'm going to be showing you a DASD management utility for finding out where all your space is. So I'm not going to answer it directly now. It's coming up, but great question. Okay, so what I'm doing here, I'm allocating a new data set. I'm putting it on this volume, which is a different volume. Then, in terms of attributes, I'm going to call it fixed block from 80, but here in the data set name type, I'm going to say library. It's a different type. Instead of sequential, it's a partition data set extended. Now, I allocated it, and it came back and said data set allocated. Now I'm going to allocate test 3. But this time, what I did, I actually gave it directory blocks, and the data set name type is PDS. Now, the reserved word library will give you a PDSE. PDS will give you the older PDS. Both PDS and PDSE are considered libraries loosely. Now, what I'm going to do is I'm on the 3.4 panel here, the data set list utility, and I want data set name zOS as a pattern matching. And it comes back with these 4 entries. So you'll notice the first entry, zOS, is an alias. So now you understand that asterisk alias in that volume column is really metadata coming out of a user catalog. Or actually, in this case, it's coming out of the master catalog. The aliases are in the master catalog. Then all the data sets that it found are on disk volumes. If I do an F11 to shift to the right, here's the data set organization, sequential, partition extended, and partition. They were all fixed blocked. They all had a logical record length of 80, and I let the system compute the block size. But these are empty. I haven't put anything inside of them. Now, I'm actually at the ready prompt, and I'm doing a LISTC entry, absolute name, zUnix.test1, give me all information. Well, when it did it, it says, okay, that's a non-VSAM data set. It's in this user catalog, and here's the volume that it's on, and here's that other metadata that's stored in the catalog. The creation date, if there's an expiration date, it's in there. This device type here is a bit setting, but there's a book that describes it, and basically all this bit setting is doing here is saying it's on a 3390 device geometry disk. There's another thing, metadata, inside of there called a file sequence number, and that's wrapping the file sequence number 0. Why file sequence number? What if it's on tape? Well, a tape can have a tape label. In the tape label, you can have multiple files on a tape. So it keeps track of the file sequence number on the tape if you're dealing with tape. And you ask for a particular file from that tape. Now, if I enter LISTC entry ZOS, it comes back and says, oh, that's just an alias in the master catalog. Now you understand what we did on that very first day when you typed in LISTC, list catalog. One thing that there is there's a lot of utilities. There is a Ditto utility that many shops will not let you use. In our case, what I'm going to do here is I set my profile to no prefix, and we have DU in our ISPF screen for Ditto. The Ditto utility can do a lot of things, and one thing it can do is it's a nice way to dump the VTOC and look at things. The VTOC, volume table of content. And this is the Ditto utility that I just entered, Ditto. It's been around forever. And I selected 3, work with the VTOC. And what I'm doing here, I want to list the VTOC entries. And I said I want it from this disk volume, the VTOC on that disk volume, and data set names, but sort it by name. Data set name. I could say sort it by extent. I could sort it by date or expiration date, but I want it sorted by name. Oops. So this is the VTOC sorted by name. The extent sequence number, the beginning and ending cylinder and head. Remember I mentioned each extent has an absolute beginning, it's contiguous with an end. So you know physically where it is on disk, the beginning and end for each extent. Now, so what happens when you go to the 3.4 panel, and on the 3.4 panel, instead of putting a data set name matching pattern in here, you put a volume serial number in here. All it's doing, it's going to the VTOC and listing all the data set names. DFSMS. It turns out that when we implemented this, there can be a storage administrator, and this is going to get to answer Robbie's question. There's several ways. I believe it was Robbie that had the question about where's all my disk space? How can I find it? Well, many times the storage administrator controls the physical resources, and they may tell you what to do to get to disk storage. Now, I will tell you, in tightly controlled SMS environments, you may be able to find the disk storage and even see it, but they may prohibit you from explicitly allocating. They may have taken control of the space in the unit and the volume on the DD statement. But sometimes you can explicitly allocate instead of DFSMS ACS routine implicitly doing it for you. Now, I won't describe this whole world here, but I am going to show you one of the main panels that get used by this world. Before I do that with the panel, I will let you know that they write this ACS routine. It's like written in BASIC. Pretty easy to put together, but they can do some very clever thing to actually capture JCL and make decisions based on what's in the JCL. Lots of different methods for doing this, but they determine where the physical media is going to come from depending upon the rules that were set. The ACS routine, it goes through there's a data class routine, a storage class, a management class, and then finally you get an assigned storage group that has the real media. And I'm not going to get into explaining the ACS routine. It's the world of the DASD administrator or disk administrator. Now, one thing that they do when you set up an ACS routine, they may tell you, okay, based on what we did, on the DD statement, we want you to code data class equal, and they'll give the values of what goes on there depending upon what you want to do. Management class can have a value, storage class can have a value, and the values are created by the DASD administrator or disk administrator, and there'll be a policy or procedure, and they tell you what to do. They're implicitly allocating things for you. You're not explicitly saying how much space, where I want to put it. So again, I'm talking about here's a little snippet of code of the ACS routine. Once again, I just want you to know that it's not horribly difficult, but it's a specialty that the disk storage administrators learn, and they get very good at it. Now, this is going to answer Robbie's question. And I'm going to actually show you a couple things and demonstrate a couple things before we break for lunch. Now, on our system, we have a selection on the ISPF primary option menu for the ISMF panel, Inter-Storage Management Facility. This is a panel the disk storage administrators use. Now, I'm going to be demonstrating it in a minute. If you want to follow along, you can. And also, I'm going to point something out to you that's up here. You may find in your system that you're using, they may not have a selection on the ISPF primary option menu for ISMF. But I can tell you this. If you go to =6, or you type in TSO DGT FMV01, that will invoke the panel if they've allocated things. Sometimes they'll allocate them, but they don't tell you the routine or the program that brings up the environment. That's the routine if you don't have a selection like IS. I'm going to be demonstrating this in a minute, real live. Okay, so bear with me while we go through this, and then we can all do it together. So here, I've entered the ISMF panel. Look at all the selections here. We're going to be doing some of this in a minute. But let's wrap up this session. There is a DFSMS bookshelf. You know where to find the bookshelf now. There is an introduction book in the DFSMS bookshelf. For those of you that are new, I highly recommend you leaf through the introduction. Another excellent manual for beginners in the DFSMS bookshelf is using datasets. I highly recommend you leaf through it. If you do want to understand more about how ACS routines work and all that, there's an implementing system managed storage manual. There's a book on managing catalogs. Typically, the disk administrators or DASD administrators take care of the catalogs. Sometimes the system programmers do. There's a DFSMS DFP utilities manual. There's a DFSMS DFP advanced services. These are some of the best books in the DFSMS bookshelf. So the important thing, there's a ZOS MVS bookshelf, but if you're dealing with data, that won't be in the MVS area, that's in the DFSMS area. Now the JCL books are in the ZOS MVS, but when you're dealing with data, look in the DFSMS bookshelf. So now what we've done, you know more about data set naming rules than you probably did before. You know what a partition data set, also known as a library, a sequential data set, just a data set name with data records, a VSAM data set is a faster type of access method, and it's got 4 different types, ESDS, KSDS, RRDS, and linear data set. You now understand what an extent is on disk, a contiguous area in the disk. You now know the role of the system catalog and user catalogs. You now know the role of the VTOC. Now, I did not do this yet. I did not describe ZOS-based Unix file systems. That's coming up after lunch. But just before we break for lunch, I'm going to share my screen. If you're on TSO, feel free to do the same. And follow along with me if you would like. Vance, can you see my screen on your session? Okay, I'm at the ISPF primary option menu. Now, before you do anything, I highly recommend type in TSO profile and enter. The reason I'm having you do that, and remember, enter is that control right side, unless you map your keyboard with the emulator. But if I type in TSO profile, notice in my case, I had my profile set to no prefix. Well, I can tell you this. You want to set your prefix back before you do what I want you to do. So, if your profile is set to no prefix, type in TSO profile, prefix, and put your ID. In my case, my ID is ZIBM049. The reason for that, the first time you go into ISMF, it tries to allocate something with your name. And if the name's no prefix, it may stop you from going in saying, I can't do this.
Actually, your prefix is 048.
Oh, thank you. So mine was 4, he pointed out. Mine is 48. So I'm going to do 48, and then enter. And if I want to validate that, I'm going to turn my caps off here. TSO profile. Now I can see that my prefix is set to my ID. Okay, on the panel, there's something called ISMF. Okay, if you type in IS to go into that panel, you will get a panel that looks like this. You'll observe that there's 4, 5, and then 9. There's some missing entries. Now, you don't need those missing entries, but if ever there's a disk storage administrator looking over your shoulder, you can make that person really nervous. What you do is you select 0 for the ISMF profile and enter, then 0 for user mode selection and enter. And you have 2 different user modes here. Do you want to be an end user or do you want to be a storage administrator? I have no clue what I'm doing, but I want to be a storage administrator. 2. So you do that, and you got to go all the way back out, F3, and then F3 all the way out of ISMF, back to the ISPF primary option menu, then go back in, equal IS. Now you got all of them. Now I'm not going to explain all of them to you, but let me answer Robbie's question. Robbie said, where's all my disk space on my system? There's several ways to find all your disk space, but here's the way I like to do it. You can select 2, volume, and enter. 1, DASD, your DASD volumes, enter. On this panel here, I can put my volume serial number is asterisk, but what I want to do, I want more than just the names. Do I want to acquire the physical data? Yes. Do I want to acquire the space data? Yes. And this is going to list all volumes and look at all the physical data and space data information on all volumes. So then you can enter, and you're going to get a list of all the disk volumes available to this zOS only. You'll notice, here's the volume labels, here's the free space, percent free, allocated space. Is this all? No. I'm going to do an F11 to go to the right. There's more information. Look at all that information. Lots of information. But what you can do is you can actually, I want to create a view, and I want 3 and 15. That would give me column 3 and column 15. Not very useful. That's the use attribute of private that I won't get into right now. But if I just do view asterisk, it gives me all columns. Now, when I used to have to take care of capacity, I could take all of this data and actually capture it in a spreadsheet and do DASD capacity planning. Where am I? So you can actually sort also on any of the columns. Let's say, for instance, I want to sort on 4% free. And I did it in such a way that the ones that have no space on them are up here. I could have done it also up here. You can do F1 for help, because I just did a sort. And it should give me information on it. Oh, it didn't give me as much as I wanted. But anyway, if I were to sort, and I believe I can do 4, is it ascending or descending? Let me see if I have to spell it out. Let me see if it will give me help. Yeah, so it didn't give me as much help as I want. Oh, descend. So I can just do a D or descend. So sort D. Actually, let's try sort A, ascending. Oh. Oh, N. So N, D for descending. Thank you. So now, here's ones that are 99% free. Here's my allocated space and free space. So that's one way you can look at all your disk storage. Now, I can tell you on this system that we have, some of these volumes we have as read only, because this zOS is running under a hypervisor VM. Now, I'm going to talk about that on Friday. But all of our volumes that begin with VPWRK are read-write to be able to store things there. We're going to be doing that later. There are other read-write volumes. So that's one way to look at your free space. But let me show you one other thing before we break for lunch. I'm going to get out of this, and I'm going to go to SDSF. And I'm going to type in ulog to get a user log, and I'm going to do a command I told you about earlier. /devserv query DASD, abbreviation is QD, type equal all. What shows up is all of your disk storage. Here is the unit device address, the labels, this is vital product data, the control unit it's on, the device type itself, the total number of cylinders on that device. However, what this does not do for you, it does not tell you how much of it is allocated and how much is free. But if you have operator command authority, and you can do that devserv command, which is just a display, you can get all the device labels with the total amount of storage on each one, but this does not tell you how much of it is free. The ISMF panels can tell you how much is free. So hopefully, Robbie, that's answered your question. And I'm going to go back to the chat lines here, because before we break for lunch here, are there any other questions that anyone's got before we break for an hour lunch? There's a question here in the room, and I'll repeat it.
I was just wondering, what's the real advantage of that?
He wanted to know what's the real advantage of having an alias. There's several advantages, equally important. So it's not just one, it's multiple. But I'm going to give you two of the most important reasons. One reason is, if you didn't have aliases and you put every data set in the master catalog, you are really hitting that one VSAM data set that's the catalog really hard. Okay? So you can spread out the I/O by having user catalogs. One reason. So you don't want all of your user data set names in the master catalog, because you could have many tens of thousands, if not millions, of data sets in a ZOS. So it's best to have user catalogs for performance. You can also take those user catalog metadata information and store in memory. So there's ways of doing that. But another critically important reason is to organize your user data, keeping it separate from the system data sets. In the master catalog, there's a bunch of data sets that begin with SYS1. All SYS1 data sets are part of the operating system. All SYS1 data sets must be in the master. It is some of the base operating system. If you go to a new ZOS operating system, you typically will have a new master catalog. Do you want to catalog all those data sets so the master knows about them? No. What you can do with a user catalog, with a new master catalog, you can do something called import connect. You can say import connect that user catalog. Master then knows about the user catalog. It says, okay, I know about that. I've got the name in here and I know where it is. Then you can turn around and define the alias related to that master catalog, and voila, there's all your data. So you need it to stay organized and to migrate between systems. You can just import connect the user catalog, define the alias, there's all your data. You can find everything by the system.